Good afternoon, everybody, and welcome to the Python Exchange. My name is James Powell, and I will be your moderator for today's session. Today, I am joined by our regular host panelists from BNL and SLS2, Hiran, Tom, and Dan, as well as my colleague Cameron Riddell. And we are here to welcome a very special guest panel today, Juan Luis, who, for those of you who have seen the PyData TV YouTube channel, have seen many of the talks that he's given, or have been a part of the Python scientific community, the NumPy, SciPy, or AstroPy community, well, you're already familiar with all of the things that he has done. I would like to welcome Juan, who has prepared a couple of prepared remarks to share with us today, and we'll invite him to jump right into those right now. Juan Luis?
Thanks a lot, James. So allow me to share my screen. So off we start. Well, thanks a lot, everybody, for joining today. So I want to talk about how to accelerate your Python code with Rust. But before that, we need to do a little bit of introduction. So first of all, we need to talk about whether Python is slow or not. Spoiler alert, yes, it is. It doesn't always matter, but when it matters, it hurts a little bit. Then I'm going to zoom in into Rust and why is it so easy to combine it with Python. I'm going to do a demo of an actual small project that I created to demonstrate some of these capabilities. And then we will jump to the conclusions, and I'll be happy to take any questions. But first of all, a little bit more about myself. So, well, my name is Juan Luis. I'm from Madrid, from Spain. I'm originally an aerospace engineer, but then I got passionate about coding, open source and stuff, and all my career has been around the Python programming language. I care a lot about tech communities and sustainability. I'm currently working as a product manager at QuantumBlack, AI by McKinsey, for an open source Python framework for data science called Kedro. I'm currently an organizer of the monthly PyData Madrid meetups, formerly founder of Python Spain nonprofits and organizer of the first 7 editions of Python Spain. And as James has already said, I have contributed to SciPy and PyData ecosystems, and I'm a music lover. So that's me. And now, Python is slow, you say? Well, I'm sure you've seen this table at one moment or another. It's from a paper called Ranking Programming Languages by Energy Efficiency, and it does what the title says. So it sorts the languages by energy efficiency, running time, and RAM usage. And you can see here on top is the C programming language for the energy column, and you see Rust, C++, Ada, Java, some compiled languages on top. And if you scroll down to the bottom, there's Python and Perl right there. So, you know, I always want to start with this because this, despite being technically correct, that Python on its own is slow and not very energy efficient, many times this doesn't matter. And the reason for that is that the ecosystem of libraries that are used from Python are very often not written 100% in Python. This is a screenshot from the distribution of languages from SciPy, and you can see a little bit of C, Fortran, C++, Python, and some others. And so the fact that you're using a library from Python doesn't mean that it's 100% written in Python, and therefore there's a very good chance that the bottlenecks of that are already very optimized. And so on first approximation, maybe the slowness of Python might not matter a lot for you. And yet, the fact that there are reasonable ways to get around this limitation doesn't mean that they're easy or exciting. This is a screenshot from a pull request that I sent 12 years ago now, in 2013, in which I tried to rewrite all the ints, so SciPy function to integrate ordinary differential equations that was originally written in Fortran 77, which as a young me back then was outrageous, right? Because Fortran 95 already existed. And that's what I did. And well, as you can see already in the screenshot, this got closed. It never got merged, to my dismay, for a variety of reasons, right? First of all, I underestimated the impact of backwards incompatibility, backwards incompatible changes, and I made a few of those that didn't really make any sense. But most importantly, and very surprising to me, there were no freely available Fortran 95 compilers for Windows back then. And this actually kicked off a series of events. And eventually it was not needed anymore to do these rewrites. The situation of free compilers on Windows improved and everybody moved on. So I was happy to see that actually that the pull request got closed. But, I've been caring about the topic of high performance Python for quite a while. And the truth is that there are so many ways to make Python fast. Many of you know NumPy already. There's Cython, Python, Numba, which with a simple decorator makes your Python code or a subset of your Python code quite fast. There's PyPy, an alternative implementation of Python that promises to be very fast, but that's unfortunately not very compatible with NumPy at the moment. MyPyC, and probably many others. And there's also just writing an extension in a compiled language. And each option has pros and cons. There's no silver bullet. It's safe to say that I've tried them all over the years. And, lately I was thinking that maybe what we as Pythonistas, right, dislike about compiled languages isn't the language itself. Maybe it's the tooling, the experience, the fact that we don't have good compilers, good debuggers, a good ecosystem, good third-party packages that we can reuse, and so on. And so what if there was a compiled language that was modern, that produced binaries that don't need a runtime, therefore as lightweight as possible, integrated seamlessly with Python, and had awesome tooling? And the answer is that it does exist. And for me, that's Rust. So let's talk about Rust a little bit. It's actually a compiled language that was born out of Mozilla. And what I find it very interesting is that this is taken from the Stack Overflow survey of programming languages, technologies that developers love, and so on. And top of this list, you see Python, which is the most desired languages. In other words, the language that most people are looking forward to working with, probably because of the AI craze and so on. And not far below, there's Rust, which is the most admired language. So that it enjoys lots of respect from the developer community. And so what we're going to do today is to marry the most desired language with the most admired one. And it's actually quite straightforward. I'm going to present you how. Why Rust, though? Well, there's probably other compiled languages that you have in mind. Many of those already have tooling to integrate them with Python and so on. And so the reasons to choose Rust could be as follows. So one, because there are so many awesome crates. Crates is the word that is given to Rust third-party packages like Python wheels or packages or distributions. And this is important because I care more about ecosystems than languages, because languages just get you so far. At some point, if you want to be productive, you need the wisdom of the open source community, right? Then because many great Python libraries and tools these days have a Rust core. Think of Polars, Pydantic, UV, Rough, and probably many more to come. Because the error messages and the IDE integration helps you learn, I started learning Rust mere 2 months ago. For real, I did the Advent of Code first 6 days or so in Rust, and despite claims that it's actually a language with a very high barrier of entry, it was surprisingly easy to get things done at the beginning. Of course, that doesn't mean that I had a 100% accurate mental model of everything that was going on. It meant that thanks to the error messages and the integration with the IDE, it was actually quite easy to at least get something that could compile and work and help me move forward. Also, because it's memory safe, it's one of the biggest reasons probably to learn Rust. And finally, just for fun, because it's cool. So let's go. And the interesting thing is that you can just get started with 3 steps. So I'm using the UV workflow tool for this. First of all, you can run UVX Maturin. Maturin is Python Rust tool to seamlessly integrate Rust code with Python. It makes use of PyO3 under the hoods. UVX is a command that runs some CLI tool directly, so it creates a virtual environment on the fly, similar to pipex. So if you do UVX Maturing new, that creates a new project template. It will use the PyO3 bindings at our request. And we're following the Maturing tutorial here, so we're creating this project called Guessing Game. Then we run UV-run Python. So we launched the Python interpreter. Notice that we didn't create a virtual environment. We didn't explicitly install anything. All of these steps are taken care of by UV in this case. And after these 2 steps, we're ready to actually start using the Rust code that was created by Maturing. So if we do from guessing game, import some string and then some string 2,3, it gives us 5. And that is it. It's as easy as it gets. You can try it on your own, and it just works. So let's dig a little bit deeper into what's happening here. So first of all, let's do a few adjustments on this project. By default, the template that's created by Maturing has cargo.toml. This is the equivalent to PyProject.toml, so it contains all the information about the Rust code, the dependencies, and so on. And by including that so-called feature of the PyO3 dependency, we can actually go from creating binary whales that are version specific. In this case, I was working on a Python 3.11 environment, and so the whale was specific to Python 3.11. Then we use what's called the standard ABI, or the application binary interface, which means that this whale is going to be forward compatible from Python 3.8 in this case up to all the versions that use this ABI, which is very convenient because then we don't need to be writing lots of code to cross-compile this code to different versions of Python. Then we can go and improve the project layout a little bit. I am used to using what they call the SRC layout in Python, which means that the package directory is inside another SRC directory, and then inside of that, there's all the codes. And so for that, we need to move the Rust codes outside of that. So in the end, the tree of directories would look more or less like this. And so now we have a clean separation between the Python codes that I will write and then the Rust code that's going to produce some Python functions. Then we're going to be rewriting some of the configurations so that the Rust code is in a private module. So I've named it to have a leading underscore there. There's a couple of lines that you have to change. And at this point, you can already start making use of the Rust functions from Python from your own codes. So this is how the suggested init.py looks like. So it imports everything under the compiled module that was created. And that is it. You can now start using the codes. As a final step, you can tell UV to refresh the cache every time you change any of the Rust files. This is not the default behavior, but it's straightforward. You add that line to papaya.toml, and then every time you run UV run something, a script or the Python interpreter is going to refresh the cache. So it's going to recompile the package with maturing and PyO3, and then give you the up-to-date code. As I was saying, this all works thanks to PyO3, which is a project that provides Rust bindings to the Python interpreter. We're going to zoom into the code in a moment. But essentially, you will see these lines over there, use PyO3, that bring some goodies that help you create these bindings. First of all, to define a function that is going to be exported to Python, you need to add this pound sign PyFunction line or attribute or macro at the beginning. So this takes care of generating some code behind the scenes. And then, well, before that, this is a little bit of Rust syntax, but it's important to know that sometimes we will want to do some error handling inside the function. And so instead of returning a string like this, we will be returning a string wrapped by this PyResult thing. It's not super important, but I just wanted to mention that. And as I was saying, after we have the function already with the proper attributes, then we have to register that to a Python module. So again, we have to define a function that's by default will be the name of that module. And then by calling this m.add function, we will be populating that module with Rust functions that then can be used from Python. So this all looked a little bit abstract. I hope I conveyed that it's more or less straightforward when you know what you're doing, admittedly. And so to put things in a more practical sense, let's do an actual example of how this would look like. And for this, I took an old project of mine called Polyastro, which was a Python library for astrodynamics that I was writing for almost a decade. It made use of Numba, which is one of the solutions we discussed before to accelerate the Python code, because I wanted to avoid the so-called two-language problem, right? So just write Python code. And so I said, well, let's try to take some of that code and see whether Rust would actually make it faster or not. For that, we're focusing on one specific bit without getting into technicalities. We're going to accelerate the propagation algorithm. Propagation in astrodynamics means taking some object that's orbiting some attractor. So imagine a satellite around the Earth, and then applying some time elapsed and finding out what's going to be the position and the velocity or the coordinates of that object after that period of time. So without further ado, let's go. All right. So here's my code, and I'm going to explain a little bit what's going on. First of all, I did use a generative AI tool to rewrite the Python code into Rust, at least the first pass, because I then had to do some corrections. And this is how it looks like. So I have this orbit module. This is how a module looks like in Rust. And it contains all the original functions from Python, but rewritten in Rust. And as you can see, this doesn't look too outrageous just yet. We're defining functions like this, and every parameter has a declared type, and I'm also declaring what's the return type of the function. And then optionally in Rust, you don't have to specify the return statement. You can write an expression like this, and that is going to be the return value of the function. And so all of these functions are not decorated that by function attribute that I was mentioning before. So if I keep scrolling down, then, well, this is all the original codes. There we go. And I also added some unit tests here because in the process of correcting the mistakes of the LLM, it was actually beneficial to do that. And so if I go to the Rust directory here, actually before that, I activate my environment and go to the Rust directory. I can do cargo test. Cargo is the Rust tool that takes care of all things packaging, workflow, and so on. So this is going to install a few things, and it's going to give me a very ugly error. But give me a second. There we go. Well, it's giving me a very ugly error live on stage, which was just working fine a moment ago. But long story short, what I was trying to do here is just to run the tests of the code. In any case, I will just go and run the IPython interpreter here and see if everything is working fine, which it should. When I do this UV run here, given that the Rust code was declared, you can ignore that, that's from a personal configuration. Since the Rust code was properly configured by virtue of using maturing as a build backend, that means that UV will take care of compiling the package, and then it should expose all these functions to me. So there's one missing bit that I will explain before getting there. So this lib.rs is another Rust module that imports one of the functions from the orbit module, and then it sort of wraps it with this py function here. So I'm almost not doing anything here, just passing the parameters from one place to the other. And most importantly, I'm calling this m.add function here so that I'm exposing this function to the module called road here. So if I do from roads import that function over there, there we go, this works. So I'm going to also import numpy as mp, and I have some parameters here. These are some orbital parameters that I have prepared. And then if I call this for Nokia Koi Rust and nothing broke, there we go. And we have this actually working here. Forgive the other part with the tests not working. That's actually an ongoing incompatibility between UV and maturing that goes in and out sometimes. To actually see if this function is giving me the right result, I'm importing also the corresponding code from Polyastro. And you will notice that this takes a little while. And the reason for that is that since it's using Numba, it has to compile the code on the fly right before using it so that it's available. So now I'm going to write the same function. So for Nokia Koi Numba, call it again. You notice that there's a little bit of latency, but again, it gives me actually exactly the same results. So we already see a difference. Before, there was almost zero latency. After importing the Rust function, it was working immediately. And for certain applications, it can already bring some advantages. But now, what about the actual performance? So for that, I can use the timeit magic from IPython. So if I do timeit with Nokia Koi Rust, this is going to run the function several times. And on average, this is taking 280 nanoseconds. And then if I actually do Nokia Koi Numba, then it's taking almost 460 nanoseconds. So this is actually very cool because it means that Rust is almost twice as fast as the Numba decorated version. And in fact, if I take the original function, which I can do like this by func, and I do all these parameters, this again gives me the same code, but this is the function that is not decorated. So I will time it. And it's taking a little bit more, 600 nanoseconds. So mission accomplished. We accelerated some Python codes that originally was using Numba, so it became a little bit faster. For several other applications, the speed up can be even higher. And in the case of Rust, it was almost twice as fast as the Numba accelerated function. And as I was showing before, the codes, despite some weird elements of the Rust syntax that might seem foreign for Python users, doesn't actually look that difficult because it's basically mathematical formulas and so on. All right. And so in conclusion, integrating Python with Rust is straightforward. For simple scientific codes, Rust is actually not that difficult to pick up. And rewriting slow code fragments in Rust is a very effective strategy to accelerate Python codes. So thanks a lot, everybody, for your attention. The material of the talk is already online for you to have a look, and I'll be happy to take any questions.
Thank you for that, Juan Lu. I want to now shift us into the second part of our call today, where we'll invite our host panelists to join us in an open discussion around some of the topics that were brought up in the prepared remarks. Before we launch into that, I do want to give our host panelists an opportunity to introduce themselves and to broadly opine just a little bit on some of the topics that were brought up and some of the themes that we see, as well as let all of our additional attendees know that given the Zoom platform change, there are now some better ways for you to actively participate in today's session. Here's how we'd like to bring you into the conversation. Obviously, if you have a question, make use of that Q&A widget. If you have an open comment, make use of the chat. Although in the chat, just note if you're broadcasting to the hosts and panelists or to everybody. And if you raise your hand, we can actually give you audio permissions and bring you into the conversation. So if at any point you want to openly opine, openly speak to any of the points that we saw, just click on that raise hand button. We'll give you audio permission and we'll bring you into the conversation. With that said, I do want to give our host panelists an opportunity to briefly introduce themselves and talk a little bit around some of the themes that we saw today. In fact, for each one of our host panelists, I would love to hear your immediate knee-jerk reaction when a scientist comes to you and asks you, is Python too slow for my work? Should I spend time learning Rust? We'll start with our colleague Tom Caswell from NSLS2. Tom?
I'm Tom Caswell. I'm at NSLS2 working in data acquisition detectors. I'm also the Matplotlib project lead. I think as to the question, my first answer would be Python's probably fine for all the reasons Juan mentioned of like the expensive stuff has been optimized in some way. But that to actually answer the question correctly, I would need to understand what they're doing and profile the code and figure out where the bottlenecks actually are. If you spend time making 1% of your code 100x faster, you have made your code 1% faster without actually like benefiting anything. So you need to make sure you get optimized the right places.
I'm sorry, Tom, that sounds like a lot of work, and I'm just looking for a silver bullet. We'll move to Dan Allen next. Dan?
Yeah, sure. I think the first step, excuse me, I was taught C++ before I was taught Python, and what I learned entering the Python community is the first step should always be figuring out what the name of the thing is you're trying to do in NumPy or SciPy, because there's a very good chance it's been written, and those implementations are going to be tested, which is maybe even more important than optimized. They'll give you a right answer that also happens to be fast probably written in Fortran or C. That hasn't changed. You should go find that function in Empire SciPy. But then you do find, like the example one we showed, that where there's some interesting math that can't be trivially reduced to a sequence of NumPy or SciPy functions, and that's where you can be thrilled to find that you have an opportunity to go learn something new. The answer used to be write a C extension, then maybe Python or Numba, and now we can add Rust to the pile of things to try.
And Dan, of course, if you'd like to briefly introduce yourself.
Oh, sure. Sorry. Dan Allen, NSLS2. I antagonize Tom and work on the Blue Sky collaboration.
We'll move over to Huron, another one of our colleagues from NSLS2. Is Python too slow for work? Should I spend time learning Rust? Huron?
Okay, let me start by introducing. So I'm also from NSLS2, and I work with Dan and Patrick and Tom, and most people here. So yeah, what I do is data analysis and workflow integration. But going back to the question, so I think like my journey has been start very slow with like very slow tools like MATLAB sometimes, and then to NumPy, and then realize no, I need more performance, and then I go into CUDA and sometimes CUDA assembly, and that has been my path. But I always like Rust. This is going to be a very shallow comment, but every time I do something, if there is a Rust tool, I tend to use that. But I like writing in Python.
And then we'll move on to Cameron and open it up for general discussion.
Hello, everyone. My name is Cameron Riddell, and while I'm not directly affiliated with NSLS2, I do see much of Dan and much of Tom along other things that I do. But is Python slow? My honest answer is no, because most of the scripts that I run, they're not taking days to finish. They're not taking even hours to finish. And the only difference for me is if something's fast to slow is, do I have enough time to get up, get a cup of coffee, and come back? And if the answer is yes, it's probably slow. If the answer is no, then that means it's running fast enough. And so that's my primary concern here. And I actually have never used Rust before, Juan, so this was a great stepping stone in that journey.
That's a great segue. I want to start off the discussion with a very controversial little piece that I think Juan Luis slipped in at the very end, the suggestion that maybe Rust isn't that hard. Honestly, I feel like we're still in the midst of a lot of scientific staff, Beamline staff in particular, still struggling to really feel like they developed comfort with tools like Python. Is that really something that we believe, that Rust is maybe just an easy next step once they have Python down? Or is there maybe a bit more of a leap required here?
Yeah, it's a good question, and it all depends on your expectations, right? When I started to learn Rust, I thought it would be nearly impossible to, get started without spending a lot of time studying up front and so on. And it was surprisingly easy. But then you're right that the moment you want to write code that is more complex, it does get hard. There is a learning curve, so I don't want to diminish that. But, again, as I said, I have mere weeks of Rust experience, and I was able, with a little bit of help from LLMs, to get something going. And that actually made me a little bit more optimistic.
Does anybody else want to broadly comment on their thoughts here, Tom?
So I say I've not written any Rust, other than I think I did a Hello World a couple of years ago. But I have ended up reading some Rust, and I found it surprisingly readable given the reputation of I believe they're called macros in Rust, allow you to extend the language in really wild ways. So they open up a lot of fun things, but you can still probably, you can read it and suss out what the code is trying to do.
Dan, did you want to add something onto that?
I had a question, actually. So we've thought about, it's come up whether we should rewrite parts of our stack, especially the services side that scientists are not directly digging into the code of in Rust. And we have collaborators at other facilities that are taking steps in this direction. And I wonder, what's the maturity of the SciPy stack? How's the TIFF reader? How's the HDF5 reader? How's the Apache Arrow support? What's your impression?
Yeah, that's the key question to ask. So, first of all, I don't think it's worth rewriting something that's fast already. Like, if there's some Python code, as Cameron says, that already gives you peace of mind because it just lasts the time that you need to grab a cup of coffee, then no need to rewrite it. If there's already some C++ or Fortran code that's fast enough, then absolutely no need to replace it. But then maybe for new projects, it could be an interesting thing to do. And it doesn't conflict with all the compiled code that you have. When it comes to the ecosystem, I found some surprising bits. So, for example, the libraries that I was using today to kind of be able to pass NumPy arrays to Rust code and back is based on a Rust package called NDArray, which is quite inspired by NumPy. And upon digging a little bit into the issue tracker and so on, I found that it's actually not quite maintained. These days it's looking for maintainers, which was not a very good surprise to see. It's very unclear to speculate how the project is going to evolve in the future. But yes, Rust is a much smaller ecosystem that's just barely taking off. And so it's a little bit rough around the edges.
Now, we do have a question from one of our other participants. Justin asks, is the takeaway from the talk Rust better than Numba? From Juan Luis' perspective, under what circumstances would it be beneficial to give Rust a shot versus using Numba, Python, or a built-in library?
Yeah, so I don't want the takeaway to be that Rust is better than Numba because the answer is it depends. I've been using Numba since day one, since Travis Oliphant announced version 0.1 in 2012 to great success to take some Python code that was mostly numerical and accelerate it with virtually no effort. And so for that use case, I absolutely recommend it. But of course, there are some features of Python and NumPy that are not supported in Numba yet. And also debugging some Numba code could be a little bit hard because the moment it's compiled to LLVM, then it's a little bit of a black box. And yeah, there's other solutions. Python, I was never a Python person, but it's very widely used in Pandas, for example, and many other projects. And so, yeah, I think when it comes to performance optimization and so on, what I tell people is to always do your own benchmarks because trusting somebody else's benchmarks is always a very tricky business.
What about for deployment? We often live in these very different environments. Like, for example, NSLS2, the code that you deploy through very formalized mechanisms using Ansible or whatnot is very different than the code that just sits on somebody's computer that they wrote for themselves, that they deploy by emailing it around. Is the Rust approach a better approach for the former versus the latter? What happens when somebody gives you a Git repository and they say, oh yeah, you need to type all these compiler commands to get this. And by the way, some Beamline scientists are still struggling to figure out their way around things like the interaction between pip and conda, much less some of these newer tools.
Yeah, indeed. I think the topic of tooling compilers and so on is always tricky. There's no way around that. And again, in the happy path, when everything works, then everything looks cool. But I had this problem, right? That there was some misconfiguration. I couldn't get the cargo test to run. And actually, I'm going to indulge myself in actually showing it just because I'm a little bit annoyed by the fact that it didn't work. So actually, if I do cargo test now, you see, now it works. It was like some environment variable that was dancing there in my computer. And this doesn't happen to that extent with Python, right? As long as you have the right dependencies. So compiled languages do add another level of sophistication and complexity, which cannot be overseen. And yet, the workflow that I found with UV and the fact that UV plus maturing takes care of compiling everything behind the scenes, I think it was actually quite impressive that it mostly works.
I'd love to hear from some of our other panelists as well as some of our other participants. But do you think the benchmark might be, if you're not ready to put the code into a GitHub repository, you're definitely not ready for Rust. If you're not ready to make sure that your code in the GitHub repository can then be packaged into a binary package on PyPI or something on Conda Forge, you're not ready for Rust. Or at least you're not ready to write code that you can share with others using Rust.
Yeah, I do agree. I think it requires some software engineering skills.
Share with others or ask for help with.
Very good, very good.
Sorry.
Because we know there's a lot of code out there. It's in Git repositories. There's not even a setup.py or a pyproject.toml. It's not quite at that level yet. And I can easily see where maybe the use of Rust could easily be something which works on my machine but doesn't work on anybody else's. Now, we have another comment from Shaker that we can address. Would you recommend Rust for numerical computations mostly? Any other interesting uses of Rust that you've seen in the wild?
So there's actually many use cases where Rust is shining. For example, if you've used code formatting tools in Python like Black, I don't actually remember how the others were called before Black, but I know there was. Yeah, so RAF is like a new alternative, right? And it's written in Rust. And the fact that the file system operations are so fast means that it can go through thousands of files really, really quickly. And so the latency is actually quite low. And I've heard, but I cannot prove, that it's used quite widely in the blockchain ecosystem as well. So yeah, definitely for things that are like systems programming, low-level programming, it's actually quite compelling. But yeah, I'm personally looking forward to using it for numerical code more.
Maybe I'll pile onto that answer and say I see online it getting used in embedded environments following that hobbyist community. And you can easily imagine that in places where you could barely fit Python and you might have MicroPython, Rust is appealing. I wonder if that will show up in a professional context for us for these device in programs that we have on some of the hardware. I don't know, that they tend to be more conservative, but it would be interesting if that started showing up.
I think an advantage Rust has over other compiled languages is that they started with a package manager when they built the language, and they kind of built everything around that. And my understanding of the model of the binaries it produces is that I don't think there's a Rust version of an SO that you then install that then you run your runtime link against something else. What comes out of Rust is a fully statically linked blob that doesn't depend on anything else. So if you need to deploy small tools in environments that you have very little control over, I think Rust provides a path by it doesn't fail to play well with others by just not playing with others.
I have an open question for our participants or our host panelists or our guest panelists. On the beamlines or in the other facilities you operate, do you have instruments that don't have operating systems? Is there a use case for, Rust without an operating system, bare metal? Is it even possible? Can something speak epics without an operating system?
Epic started in that context.
Okay.
But yeah, we do have devices that run straight on the hardware.
And so maybe there are some opportunities to use Rust in that fashion.
I think Jacob Philic let us know that the Diamond Light Source, which is the peer facility of ours in Oxford or outside of Oxford, is running Rust in distroless containers for small services. which I think is, I've never used a distro's container, but I understand container, no operating system.
I mean, it'll take the kernel from. No, I don't. I mean, if they're talking about a OCI type container, it takes the operating system from the thing that just doesn't have any file system, I'm guessing.
I see.
Right. So here we'd be talking about something that's really, truly bare metal, like it doesn't even boot, it goes straight into the single FE binary or whatever the heck you do.
Yep.
And it's interesting to hear from Tom that in the original Epic's design, that was the kind of device. But now, how hard is it to get 128 gigs of RAM on a machine? I don't know. I have another open question, which is about the design of the interplay between your Rust and your Python. It occurs to me that the operating mode that we're still in Python is this heterogeneous environment where you have Python for flexibility and generality, and you have compiled code for specific little units of functionality. But it seems like with all of the various approaches that we've been given, Numba, Python, extension models, Rust, nobody seems to really be talking about how do we design for that. And my analogy, or at least the motivating example that I used to think about this is, if you asked me to design a simple game of billiards and to make it as fast as possible, to make that simulation as fast as possible, I could give you a single function called play entire game from end to end and code everything in Rust. And then the moment you ask me for a feature request like, oh, when one ball hits the other, simulate this one additional detail, then I can't do anything without digging into the Rust code and changing that. I've lost all generality whatsoever. And on the other end, I could do this incredibly incrementally and do individual collisions being called from the Python code, but then there's no guarantee that the overarching Python code doesn't slow everything down, so that my one little collision function, it's fast, but the whole program is about the same speed as before. How do you actually design for that right balance between generality and specificness when you have these powerful tools so you actually get what you're trying to get out of these? And as an additional motivating example, I think if you wrote the entirety of Blue Sky in Rust, you probably wouldn't actually get any real speed up. At least the planification stuff, any real speed up in practice.
It's a very intriguing question. Like, one of the times I saw Richie Vink, the creator of Polars, this data frame library written in Rust, he said, look, I love Rust, but not for doing data analysis. Like, he doesn't do data analysis with the Rust part of Polars. He does it with the Python part of Polars, right? So there's indeed this tension that you're mentioning. And I don't really have a good answer for that. I think the Julia folks tried to do everything, right? To achieve this speed of having a compiled language while at the same time having a good interactive experience and so on. But yeah, I'm not a Julia person, so I cannot really comment on how that is working out.
My view of Julia was they were aiming for a homogeneous environment, so all the code would be in Julia, and so the difference between your program structuring code and your computational code, well, it's all in Julia, which is a very different thing than Python, which says, in Python you do all your glue stuff, and then you do all your fast stuff or your performance sensitive stuff in whatever compiled language.
I have maybe somewhat of a related question here. So it's probably not surprising that as a compiled language, the compute is more efficient and faster on Rust. But I was quite surprised when you said the file operations are faster, because usually the language is going to rely on system calls anyway, I think. Why is file operations faster in Rust compared to a language like that?
Sorry, I didn't quite get that. Why is what version faster?
Oh, you mentioned the file operations like disk operations and like that's like I/O, but a language like Python is not actually going to go and do that. It's just going to rely on system calls to do the file operation. So how would Rust be faster in that sense in that particular case?
Yeah, I think you're probably right that in the end it boils down to very low-level file system operations. It probably the reason I think Rust is so fast at this is because, the inner loop is also written in Rust, right? So, for example, if you're iterating over a series of files in Python, you will have to go back and forth between the system calls and then, I have this huge path object in memory that has all these many properties and so on. Whereas in Rust, abstractions are very lightweight, and so you can do these low-level system calls, but the iteration over many, many files is going to be much faster as a result.
Tom?
It is my understanding, which I could be wrong, that a fair amount of the speed up also comes from parallelism, right? Python is doing all of the system calls sequentially, whereas in Rust, because you don't have the GIL, you can just blast them out, kick them all off at once, and wait for them to come back.
Now, we have one other question from our participants. I've heard some complaints, an anonymous participant shares with us, about a so-called borrow checker, especially for no users of Rust. Could you please explain something about this to a total novice?
Well, I'm not a total novice, but I'm a novice, so please don't take this explanation as gospel. But in Rust, one of the core notions is that every value, right, any area of memory has to have a very specific owner, which means that when you're passing a variable from one function to the other, then the ownership of that value changes. And this mechanism, which is what makes writing Rust somewhat annoying sometimes, is what powers actually the memory safety features of the language. And there's lots of extra things around that, such as passing a reference, so not giving away the ownership or managing the lifetime of the variables and things like that. That gets a little bit complex. But the gist of it is that, there shouldn't be more than one owner for some value in memory, so that when you free that value, right, you're sure that you're not freeing it for anybody else that needs it. I hope that makes it for a decent explanation.
And I think it's worth noting that, ownership exists in Python as well. It's just that we never really pay that close attention to it. A generator you can think of as a linear or affine type of a form. And so you have to at least document what owns the generators and who's consuming them. There's just nothing checking that for you.
In the wake of the White House letter about a year ago saying we recommend memory-safe languages for important applications, we sent one or two people to CPPCon, which is apparently a very exciting CPPCon to be at, where the community was ripping itself in half over what to do about this. And one view was, well, we do memory safety simply by writing bug-free code. Do you imagine that? Do you imagine that could be grafted onto languages that don't have it, or when you see it in the way it works out as you're writing Rust, is it clear that has to be built in from the beginning? I don't know if you have any hot takes on this.
It's a good question, actually. If we establish a parallelism with Python and typing, I think it's very clear that Python was not designed with typing in mind.
It's a great comparison.
And so adding that does give you some benefits, but it always feels like it's not quite a match, And on the other hand, for example, enums in Python, I'm always like, how do I make effective use of it? But then enums in Rust, because of the type, the strong types, and because of different features of the language, they make a lot of sense. And so, I think retrofitting certain things in languages that were not designed for it is always hard, and you'll always be leaving some gaps, let alone, all the backwards compatibility history that you have, and so on. So, right. I think it's a good debate to have, but probably the biggest limitation is getting past that mentality, right, of thinking that you're able to write bug-free code, which unfortunately none of us can do.
Did anybody find it a little bit odd that when the memory safety thing became a rallying cry, nobody spoke up and said, well, hold on a second, Python and Java are memory safe, let's just use those?
That's how I read it.
With that said, I see that we are coming to the conclusion of our time. Of course, we do have time for one or two other comments or questions, so please do raise your hand or add a comment to the Q&A widget. In the absence of a comment, I'm very curious, Juan Lu, as you were learning Rust, you mentioned the use of the LLM. Did you have any special tricks that you used to accelerate your learning, to use the LLM as a tool to help you learn as opposed to just write code for you?
Yeah, I have one tip, which is don't trust it. Like, I'm sorry, but LLMs are very dumb, at least in 2025. Maybe in 2026, they become self-aware and so on. But at the moment, they're very silly. And so, I spent literally a whole day debugging some code that was produced for this talk. And the only problem was that some parentheses were out of place, and this was all the LLM's fault, So had I written the code by hand myself, who knows, maybe I would have spent less time. So yeah, my tip is actually be very careful with the autocomplete. Read what you're writing, even if it's the LLM doing so, and do write some tests, please, because this is very tricky.
With that said, as we wrap up our time together, I would like to ask our host panelists for any final thoughts or comments. We'll go through each of our host panelists, Tom, then Dan, then Huron, then Cameron. Tom, any final thoughts or comments as we adjourn?
To reiterate, if you're looking to optimize code, always profile and benchmark first and figure out where you're going to get the biggest gain in the overall runtime, which is the thing you actually care about for your effort.
Got it. If you're looking to optimize your code, give it to Tom to profile so that he can optimize it for you. Dan?
Yeah, can't say better than what Tom said. I think I'll use my time to thank Juan Luis for exposing us to Rust. That's the first time I've seen it run against NumPy and Numba doing the same thing. It's cool to see the beginnings of that.
Huron?
Yeah, thank you, Juan. And also, I think I just want to mention, I think tools like Line Profile, I forgot, are really great tools for making your code run faster, and that way you can identify quickly which parts are slow, and maybe that could be a bridge to using language like Rust.
Cameron?
I don't want to harp too hard on the fact that we've all said that make sure you really need to learn or use Rust before you go off and learn it. Because when you start getting into the world of lower level languages, with Python, you have your business problem, or you have the script that you're trying to solve. With a lower level language, you have the business problem, and you're also going to be wrestling with the computer at the same time for those compile errors. So I'll leave it at that, but I think this is another just reiteration of make sure what you want to do is really not already supported by NumPy, supported by SciPy, especially if you're coming from a Python perspective.
And when they're ready to learn Rust, Cameron, will you be there ready to teach them?
Absolutely.
Fantastic. I want to give Juan Lu our final comments for today's session. Juan Lu?
Well, so my final comment is you don't need any excuse to learn new languages. It's always fun. It's like learning human languages. It always opens up new possibilities and makes you a better developer as a result. And just echoing what Tom said, don't follow any fancy trends. Use the best tool for the job. Do your own benchmarking. But other than that, have fun.
With that said, thank you all for joining us, and we'll see you next time.